Hello everyone, my name is Floyd Chitalu and this is Simulating Brittle Fracture with Material Points. The goal of this research was to produce a meshless crack propagation scheme for fracturing of highly stiff materials. In essence, what we want is to simulate physical breakage with branching cracks in a meshless fashion during propagation. This is an example of what the final result looks like from our mesh-free crack propagation scheme. There has been a lot of great research in this direction. The most expedient techniques are the geometry-based methods. The basic idea is to decompose a volume into convex parts as a pre-process, which will then determine how an object breaks at runtime. However, this approach only offers predefined breakage patterns, followed by topology updates to mimic the physical breakage. Alternatively, there are stress-based methods that use meshes and offer physical accuracy. Here we find finite element and boundary element methods, which discretize equations of continuum mechanics. In practice, however, implementations require mesh updates to extend the crack during propagation while also needing linear system solves. Also, incorporating phenomena like branching is tricky, where crack bifurcation is at best a side effect of interior surface intersections from the domain boundary. And finally, we can also use point-based methods, and I'm trying to convince you that this is a good idea. These offer a mesh-free simulation of elastic deformation, which will be convenient. However, there's a tendency to suffer from numerical artifacts like artificial plasticity, and performance is an issue. I would also like to point out this paper here, which gives good background to the material point method details that I'm going to glance over in this talk. I'm essentially going to argue that previous methods are limited in their modeling of branching crack behavior on a combination of thick and thin volumes. So then for the rest of this talk, I'm going to have three parts. First, I'm going to summarize why we use material points. Then I will introduce the idea of continuum damage-based fracture and how we model crack propagation using points. Finally, I will show you how we can get thin, non-manifold crack geometry from simulated damage. Let us get started then on material points. What we will do is take this object with a Neumann boundary condition on the left and some smeared damage in its volume, which is shaded in red. We then essentially want to ask ourselves the question, what is the stress at each local region of material given this boundary condition and the current damage state? For now, let us ignore the damage, and all of our degrees of freedom are the positions of point samples of the domain volume. These points themselves currently just represent healthy, undamaged parts of material. We are also going to introduce the notation of V and M for velocity and mass respectively, which will give us the momentum at each particle. In general, these variables are used to advect particles. They're used to advect particles using the conservation laws of mass and momentum. Note too that since we work with points, there will be no cumbersome topological meshing for propagating cracks with triangles or tetrahedra, etc. Now, we're going to formulate force functions according to this grid. And at each grid node position, we will sum up all of the change in momenta of the particles in its neighborhood. To emphasize this point, I have also introduced the notation of I and P to denote nodal and particle quantities respectively, like positions. And then, the forces needed to define a time dynamic simulation can be written like this. Basically, the internal elastic force vector F at the grid node I is a function of several particle quantities and its position. Detail about most terms can be ignored here, but I would like to point out the deformation gradient F, which quantifies the local distortion at a given particle and then also determines the stress matrix as well. And now the idea is that the fracture problem can be defined in such a way that the only property that matters about the nodal force due to each particle is the amount of damage on that particle. And this means that we can adopt any standard material point formulation with little to no modification to be able to simulate fracture. So we will only need to modify the stress to incorporate the effect of damage, essentially. So how can we include fracture in our formulation then? Let us put the crack back in, which will now be represented by damage on the material particles. You will notice that we have a smeared path with some thickness here, but we will extract a thin surface from it later. The unknown quantity that we're going to determine in our simulation is the per particle damage, which I'm going to call C here. And to do so, we extend the definition of particle stress according to the coloring of the particles on the right-hand side. And I'm also going to introduce the following notation. As you see, the particle stress is now a function of our new degree of freedom, which is the damage variable. Thus, the scalar variable C here that is highlighted is new according to our fracture. And so when the crack grows, we're going to have more particles with damage. And then the highlighted variable in the equation will increase accordingly at each deteriorating particle. But still, the node of force itself maintains the same analytic description, which makes our method convenient because it requires little change. So then to answer the question of why do we use material points? Well, besides the fact of being meshless, which saves implementation effort, we can easily incorporate the influence of our quantity of interest, which is the new internal state variable that represents the local damage. Also, we can more or less have a similar analytic description of force as in the case where we are concerned only with elastic deformation, which is convenient. Now that we have this description for how to compute internal force given the damage, how can we use this then to simulate fracture? An evolution law will quantify how damage itself develops as a function of stress due to deformation, which is the Rankine model. Here, the axes represent the principal stress directions. Green shade is the region where a particle undergoes purely elastic deformation. And outside of this region, the stress is weakened, which is governed by a maximum principal failure threshold. Damage itself is determined by the ratio of the effective tensile stress to the principal failure threshold. This gives our evolution law, where the variable h is related to the material properties and also the background grid size. We incorporate damage by weakening the tensile stress, which is the component providing the load necessary to separate material. Finally, the stress is then reconstructed based on the modified tensile component, or its magnitudes, and the corresponding direction vectors. Our next question then is, what happens when we try to propagate cracks according to this formulation alone? What happens is this. Basically, it works, but the damage tends to be exacerbated to the point where discernible crack paths are lost as the material weakening spreads throughout the domain. You wonder why this happens. The reason is we have artificial welding or sticking together of particles in regions where there should be discontinuities. Essentially, we have particles that are seemingly on opposite sides of the crack, but because they remain within each other's influence radius, they remain coupled. So then how can we avoid this? If we can assume for a moment that a crack surface exists, then we can use its location to separate particles and grid nodes. A particle P will belong to one of two velocity fields at the grid node I according to the relative position or location with respect to the crack surface itself. One example of a field quantity that will be transferred between particles to grid nodes is the momentum, which is used to compute derivatives for stress-based force evaluation. Each grid node that is within kernel radius from the crack will now have two velocity fields, and each receiving contributions from the respective particles. Thus, node of force contributions come only from the particles on the same side of the crack surface. As you can see then, when we apply such a scheme, a discernible smeared crack path is now recovered, which is ideal. So far, we have assumed the existence of a crack surface to ensure that our field variables are discontinuous due to damage. Let's now look at how we can define a crack surface geometry from the damage field itself. Going back to the bunny model that we saw before, the problem that we wish to solve is that of disambiguating a surface from damaged particles. Basically, what we want is this, which is to place a thin surface amidst the damaged particles for treating the material separation. To resolve this, we approximate crack geometry using a Voronoi tessellation of the damaged particle region, which will give us a medial surface. And we do this by essentially splatting particle damage values onto a grid, which then determines the boundary of a damaged region. The grid nodes bounding a damaged region are then used as input sites for a Voronoi tessellation. A schematic representation looks like this, where the medial surface of the damaged area is the crack surface geometry itself that we're looking for. In general, we select the faces of the medial surface by querying the Voronoi cells of grid nodes and their neighboring cells to get the shared face. And then on this shared face, we determine whether it belongs to the medial surface if it is in a fully damaged region, which we determine by sampling damage values on the grid. So let me summarize our method in this example. What we have here is a bunny with intentionally exacerbated damage from simulation and with several bifurcations of the damaged paths. And then on the right-hand side, we have the non-manifold surface geometry that has been extracted from the smeared crack path itself. Now, essentially what is happening is that we start from our material particles, we then update the simulation to propagate cracks with per particle damage. Then we use a medial surface approximation of the damaged volumes, which will give us the explicit crack surface geometry that we then use to cut this object that you see on your screen right now. In line with the theory of fracture mechanics, we can also reproduce the expected behavior of the 3 fracture loading mode tests. Here, a mode of fracture simply just refers to a decomposition of crack tip stress into one of 3 force components that's shown on the top left. Now we can also do the exact same simulation, same boundary conditions, same geometry, except that we can also use damage gradient fields to emulate a large variation of results. Details about how we do this can be found in the paper, but here I show you a few examples. For a pre-notched rectangular plate test, we produce expected propagation behavior, which is also consistent with mechanics literature and is ideal for physical accuracy. However, our method does show some resolution dependency, which affects crack thickness and propagation speed. In this case, the equilibrium of elastic energy, fracture energy, and the prescribed boundary conditions is reached before the cracks finish propagating to the boundary. This is not a practical issue, however, as most cracks generally tend to reach the boundary. And then also, crack thickness is not an issue because our thin surface approximation is robust to severe expanses of damage. This is a result with a little bit more action going on, where we couple with a rigid body engine. And as you can see, there are lots of fragments of different sizes, and you can see the fracture patterns on them as well. This is about 3 hours of total simulation time, including the rigid body collisions and dynamics, which is significantly faster than other NPM simulations. A key part of our speedup when compared to methods like CD-NPM is that only crack propagation is resolved with continuum damage mechanics. Our propagation model also has little to no elastic deformation, which allows us to use a much smaller number of particles as well. So to summarize, I have presented to you a mesh-free crack propagation method using continuum damage mechanics with locally defined damage updates. And this is achieved by combining an adaptation of a material point method and Voronoi tessellations to define thin embeddings of geometry on the smeared crack paths themselves. With this, let's look at a few more examples of what we can do. And what we have here is a simulation of shattering thin glass. And here we visualize the propagating crack surfaces, which we extracted from the damage. And this is a variation of the lion statue demo that we saw at the beginning, where the lion and column are smashed into pieces following collision with a billiard ball. With this, I will thank you for your attention. You can also find our source codes online. Thanks very much.